All right, welcome to the final installment in our discussion about solving linear and nonlinear inequalities. And in this video, we're going to wrap things up with a discussion about solving rational inequalities. So, if we are thinking about how we solve polynomial and absolute value inequalities, rational inequalities have a lot of the same components, but there are two main changes, okay? Now, a rational inequality will be an inequality that has an expression that has a variable in the numerator and the denominator. And so you're going to first do exactly what you did before. You're going to relate that inequality to 0. And then what you're going to do is take that numerator expression and set it equal to 0 and solve for x there. Okay, that's going to find you any boundary points that are x-intercepts. Then you're going to take the denominator expression, set it equal to 0, and solve for x. And that will find any boundary points that are undefined. Okay, so that's where the graph does not even exist. There's probably an asymptote or a hole there. Okay, so now the other steps that we used before, number 3 and number 4, are exactly the same. The only thing that is different is we need to be really careful when we get to writing our solution. And that is because if your inequality involves less than or equal to or greater than or equal to, we need to be careful because our denominator cannot equal 0. Remember, we can't divide by 0. So we want to make sure that any interval that includes the boundary point or points that comes from the denominator will use parentheses, okay? Everything else will use brackets. Any interval that includes boundary points that comes from the numerator will use brackets. All right, so let's jump in. All right, here I have a fairly simple rational inequality. And notice that it's already set, so it relates to 0, so I really don't have anything I need to do right there. So that second step is taking the numerator and the denominator and setting them equal to 0 and solving for x. So let's do the numerator first. 3x plus 3 is equal to 0, so x here would equal -1. Now our denominator, 2x plus 4 is equal to 0, so x here would equal -2. So I can go ahead and put those values on my number line, and those become my boundary points. And then I'm going to divide up my number line. And remember, with 2 boundary points, I will have 3 intervals, the one on the left, the one between the boundary points, and the one to the right. Okay, now, do I need to be careful here? No, because my inequality is a greater than symbol. It's not a greater than or equal to, so I don't have to worry about my denominator equaling 0 because the inequality does not have the equal portion in there. So let's go ahead and name our intervals. I have -infinity to -2 on the left. Right in between those, I've got -2 to -1. And then finally, on the right-hand side, I have -1 to infinity. All right, so let's take these intervals and come up with some test values in each of them and evaluate those numbers. Okay, so let's use -5 on the left. Let's use -3/2 in the middle. Or you could use -1.1 or -1.5, anything between -2 and -1. And on the right-hand side, we will use 0. Okay, so if I use test values here, I'm going to evaluate that r of x for each of those x values. So subbing those in, I get r of -5 is +2. r of negative 3 halves is negative 23 halves, and r of 0 is 3/4. So I want to check and see which of those output values is actually greater than 0. And if I sub in a negative 5, I have that 2 out. That is indeed greater than 0. So this is a good interval. This one, not so much, because negative 23 halves is not greater than 0. And then last, that positive 3/4 is greater than 0. So that interval will work as well. So we can definitely cross out that middle interval and just include the outer intervals as our solution. So negative infinity to negative 2 and negative 1 to positive infinity becomes our solution there. So here's a graph of the rational function y equals 3x plus 3 over 2x plus 4. And if we're looking at this, we want to identify what part of this function is above the x-axis, or what's the domain of this function that's above the x-axis. Okay, and so you can see that this function from left to right goes from negative infinity, and it runs right alongside that negative 2, and that's where an asymptote is. And then the graph kind of jumps over that line negative 2 and resumes coming up from the bottom up to negative 1. And that's where it goes back into that shaded region. So we do have the domain of what is in the shaded region is negative infinity to negative 2 and from negative 1 to infinity. All right, so we've got to do one where we've got to be careful, right? So here is a rational inequality. X plus 1 over x plus 3 is greater than or equal to 0. Okay, so we're going to first write it so it relates to 0, which it already does, so don't really have to do much with that. But then we're going to take that numerator expression, set it equal to 0, and solve for x. Define boundary points that are x-intercepts, so x is equal to negative 1. And then we do the same thing for the denominator expression. And this is where we've got to be careful because that denominator cannot equal 0. So if I set that denominator equal to 0 and solve, we say x is equal to negative 3. So when I put those numbers on my number line and create my intervals, I want to make sure that any interval that includes this negative 3 boundary point has got to have parentheses because it can't include that negative 3. All right, so notice I've got from negative infinity to negative 3 with a parenthesis there. I've got negative 3 to negative 1 with a parenthesis on the negative 3, but brackets on the negative 1 because that boundary point came from our numerator, and our numerator does not have that restriction of it can't equal 0. And then our last interval is from negative 1 to infinity. All right, so let's choose some test values. Let's choose a value between negative infinity and negative 3, and from negative 3 to negative 1, and from negative 1 to infinity. Anything you want in there. And I chose these. X is equal to negative 5, negative 2, and 0. And then we will definitely evaluate r of x for each of those. And r of x is x plus 1 over x plus 3. And so when I substitute those x values in, I get r of negative 5 is 3 halves, r of negative 2 is negative 1, and r of 0 is 1/3. So now let's check those output values and see if they satisfy that rational inequality. Is 3 halves greater than or equal to 0? Indeed it is. Is negative 1 greater than or equal to 0? It is not. And is 1/3 greater than or equal to 0? And we have another winner. So we can eliminate this middle portion of the graph as part of the solution set, and just the outer portions will be our solution. All right, and if we have identified our intervals correctly here, we don't have to worry about transfer. It's going to transfer correctly. Let's look at this graph. This is the graph of y equals x plus 1 over x plus 3. And if you are looking at this graph, we want to identify the domain of everything that falls within the shaded region. And so we have this left-hand portion of the graph that goes from negative infinity to negative 3, and that's a piece of the domain. And then the other piece that is in the shaded region starts at negative 1 and goes to infinity. And that's how we get that second piece. All right, we'll see you next time, and that wraps it up for solving linear and nonlinear inequalities.